see the green icon, you can share the screen from there. And then you can do entire screen up in the top left. Okay. And then you can bring your slides in front of you.
Whoa.
There you go.
Nice. Okay.
That's cool.
Pardon the infinity, everybody out there, but we're just getting going here. We'll probably give people another minute or so to get in. Looks like we've got 9 viewers right now, and so we'll wait a couple of minutes here before we get started. And are we on the question chat room?
Yeah.
Okay, so the chat room's on. It's being monitored right now for all of you out there in webinar space. So if you have questions, feel free to jump on there, and we will have them sort of proxied up to us here as we go through talking about Wrangler. I guess that's the accurate clock, so we're actually about 5 minutes past. So that's my standard, let everybody show up. So we'll just start with introductions. So welcome everybody. This is an introduction to the capabilities and what's going on with Wrangler here. I'm joined here by my colleagues Christopher Jordan and Wei Zhu. I'm Niall Gaffney. I'm the Director for Data Intensive Computing here at TAC. Christopher Jordan is the head of the Data Management Collections Group, and Wei Zhu is the head of our Data Mining Statistics Group, which sort of make up the 2 major pieces that we have here, both for working with collections of data and also analyzing and running analytics. Wrangler is sort of an interesting system that we've been working on here for going on about 1.5 years now from the proposal till now. Wanted to acknowledge that this is funded by the National Science Foundation ACI grant listed here. So this is, where Wrangler came from. But it's a group not just here at TAC. We have several academic partners. We're working with Indiana University and the University of Chicago. Indiana University is hosting part of Wrangler for us, as well as helping us with a lot of the end-to-end network tuning and other key components of the system. And the University of Chicago, in particular the Globus group, is helping us with integration of Globus Online and some of the Globus publication capabilities to enable high-speed data transfers, as well as publication and sharing of data as generated here on Wrangler. Our vendor partners are Dell, who I think most everybody knows, and then another company called DSSD, who has been recently, or not that recently, back in May, purchased by EMC, and so now is a subsidiary of EMC, who are providing us a very interesting piece of technology, which is sort of at the heart of what Wrangler is. So Wrangler is a new data-intensive supercomputing system that we're building here at TAC. It follows somewhat, I think, in sort of in line with some of what was initially done by Gordon, but really changes, I think, a lot of what we think of when we think of a data-intensive computing system. We built it, designed it from the ground up to support a lot of the science and a lot of the I/O patterns and other capabilities that aren't supported by sort of the big classic iron systems that we have right now. HPC and big data do have a lot in common. I mean, they're all running on computers, ones and zeros, and those sort of things. But the overlap between those really isn't 100% in all applications. And not everything runs well on an HPC system that would run well on a Hadoop cluster, for example, and vice versa. And so Wrangler was sort of fill in part of those gaps. It's also to be able to allow us to work with the large amounts of data that are generated not just by the world around us, but also by the computational problems that are being run on HPC hardware such as Stampede. We're working to bring together these new technologies to bridge some of these shortcomings or areas where we really are not optimally able to work with the data and information that's out there to sort of bring together the capabilities of data and HPC clusters. Of course, clusters aren't anything new. We've been building them for quite some time. The initial early data clusters go back to the Beowulf project back in the early 90s. Soon thereafter, the Google folks at Stampede, the Google folks at Stanford, wrong S word, at Stanford, put together the first sort of data compute cluster. And while all built on commodity hardware, they did have some different design features. And really, at the core of the differences between these systems was the read-write access patterns. Google, of course, has more of a MapReduce environment where you have a lot of local storage, which is optimal for doing many file and sort of smaller file access patterns, whereas a lot of the clusters that we have today are much better at working with large sequential reads and writes. And that's sort of the difference between having a system based around centralized storage versus a system based around local I/O. Mixing Hadoop on today's HPC hardware really is not a good idea. There are people who try and do it, and there are people who very often sort of crash a Lustre metadata server or do something else nefarious. And it's really not encouraged to try because the two things are not meant for one another. But often you may need, both sorts of access patterns within a workflow. And so that was one of the things we were trying to work with here with Wrangler, is to allow you to have, sort of the best of both worlds. It's not just about data research, though. Here's an example of sort of a biophysics job where you can see where the arrows are pointing. The first arrow is pointing basically to the load on the file system on the metadata server, which is going up when there's high I/O. And the last curve down there is showing where the CPU utilization is going down because you're sitting waiting around for your I/O to take place. And so a job that might have taken only 4 hours here to complete took almost 7 hours to run all the way to completion. Other jobs are even more nefarious than this. Here's one that starts off fairly good, but never really gets going as far as its I/O. I mean, as far as its compute, simply because it's bound by I/O. And so this 2-hour run is probably something that should have been packed into a third the time were it not for the I/O limitations of the system. So the goals of the Wrangler project are sort of to address these I/O problems, to allow you to have a system that works with big and small data in a reliable and secure way. So having data available with both I/O patterns, but also replication and secure storage. Lots of different data types are core to this. So having both structured and unstructured data allow you to work sort of in what I think of as more of a classical style, which is your structured data style, but then moving into what is the sort of the nominal big data idea of unstructured data. Fast, but not just fast for particular I/O patterns, but fast for being able to do sort of transactional reads and writes, which are the cornerstone of a lot of data apps. Built to support Hadoop, but not just Hadoop, because Hadoop is merely one of a many number of workflows that support data compute, including supporting languages such as R, supporting GIS databases, other databases, and other perhaps less scalable things based on languages like Java, and really to try and flesh out a lot of the capabilities that don't run very well on either a classic Hadoop infrastructure or on a large machine like Stampede. It's also part of the job is to analyze and build the data, but really we also want to be able to support the full data life cycle system, so that we are doing things not with just a scratch-based file system, but with a file system that will continue to house and work with data over the life cycle of the entire system. And so this is not a scratch-based file system like Stampede, much more of a curated system where there will be some tools available to people to collect metadata and manage the data that they are producing or analyzing on the system. At the heart of Wrangler is really what is a small cluster by today's standards, very similar, to what we've been doing with Stampede here. We have a 10 petabyte file system that is interconnected by way of InfiniBand FDR non-blocking network, bringing that storage system to bear into 96 nodes of Haswell processor servers here at TAC, each with 128 gigabytes of memory and 24 cores connected to the Ethernet fabric here by way of 40 gigabit per second Ethernet connectivity. The sort of special sauce that we'll get into here is the high-speed flash storage system, which is connected to the analytics system by way of PCI. And this is sort of the area that will get you past many of those I/O bottlenecks. We expect to get to a terabyte a second I/O rates across this small cluster to this high-speed storage system, and somewhere in the area of 200 million IOPS net. We said we also wanted to make sure that we were reliable and redundant, so we have a secondary storage system at Indiana, connected again by way of IB to a smaller analysis cluster of 24 nodes, identical hardware and configuration at Indiana. And these are all then connected by way of both of our 100 gigabit Ethernet 2 connection, which will allow us to replicate the system as well as have jobs running in either place. In addition to that, this distribution allows us to take advantage of that 100 gigabit Ethernet 2 or Internet 2 connection at both sites for both ingest and for retrieval of data, so that we will have higher availability than any single site would allow us to put forward. Storage system is basically a large storage system very similar to what's on Stampede, 10 petabytes of Luster on 34 OSTs using the new 6 terabyte drives. As I said, networked by way of the Mellon XFDR, replicated between the two sites, and exposed to users in sort of two fashions, and Chris will get into those in a little bit, but as a traditional sort of Unix-style file system, as well as an IRODS-based data management system to allow people to work as they need with one or the other, or both of those sorts of forms of storage. The analysis hardware is the sort of very new Intel Haswell core system coming, which came available a couple of months ago. Each of these will have the 128 gigabytes of RAM connected by way of the 40 gigabit Ethernet. At 96 of those nodes will be here at TAC, and the 24 nodes in Indiana. And sort of the special sauce here is the DSSD storage, which is, this is something new and something different. This is not SSD storage, which has been used in the past. Rather, it's PCI connected flash, which is available across the multiple nodes, and in fact will be available across all of the nodes within Wrangler. It is connected directly by way of PCI, so there is no disk-based interface between you and the storage to slow things down. The access is directly from the CPU or other PCI devices directly to the flash storage. Multiple nodes will have direct access to the same storage, so this is a many-to-many environment, not a individual SSD in a particular node then shared by way of other methods of data transport. It'll have a half a petabyte of usable space, which is made up of nearly 100,000 NAND flash drives. Initially, there will be 480, and in the long run, there will be 960 Gen 3 PCI links between the storage system and the analytics cluster here at TAC to provide those very impressive numbers of 100 gigabyte per second and 200 million IOPS to users. We have a small version of some of the DSSD hardware available to us right now here at TAC, and we've been running some tests. And these are sort of some initial, while most of the actual numbers themselves are still under NDA, the curves are sort of the impressive parts. On the left, you see sort of a single node comparison of the DSSD storage doing read and write of different access pattern sizes ranging from 4K up to 40 megabytes. Compared against SSDs. Now these are SSDs attached by way of a SATA interface. And you can see that even at the 4K IO pattern, that the performance of the DSSD is much better than what you'd get with standard SSD technologies, and it very quickly becomes excessively better, I would say, as the reads and writes become slightly larger. I didn't plot on here. We did compare this to what regular spinning disks have. It's very hard to see that because it's a little tiny blip on this plot, but if you look at it, regular spinning disks don't start to shine as far as their I/O until you get to that 400 kilobyte and even the 4 megabyte I/O reading patterns, which is why many of the Lustre file systems favor your large sequential reads and writes. Multi-node is also something we've been working with, is how when multiple nodes are accessing the same storage, how they are able to increase I/O in parallel, and that's what the right-hand sort of graph is showing again that for 4K and for 8K I/O patterns, you see you're paying a slight penalty there for those small access sizes, but it's actually rather impressive where they are. And as things get larger and larger, they start to stack up on top of one another. This really gives us hope that we're going to have a system that's going to be able to handle all these various access patterns from small to large, and give people the I/O that they need in order to do the computations that they have at hand. The flash storage will be exposed in basically 3 different methods. It will be exposed as a traditional file system. We'll have a parallel Lustre file system available across the whole cluster that all nodes will be able to access. You can also have local-based flash storage in individual block devices if your workflow requires something along those lines. It would be exposed as a Hadoop distributed file system. I love the fact that I always do that. But HDFS is the backbone for Hadoop and the other MapReduce, other Hadoop applications such as MapReduce and Spark. Initially, that will be exposed in a more classic style, but eventually, as the technology becomes as we get new releases of the software from DSSD, this will leverage the object store to give the Hadoop file system the fastest I/O possible. It's also usable as to power SQL databases and NoSQL backends. And then lastly, as this object store with the native API, which will allow people to have the highest throughput to and from the flash possible. In addition to sort of our traditional HPC stack that we will start putting pieces of onto Wrangler, we expect to have computational biology software. We'll have support for R databases, some of the NoSQL databases, and the full Hadoop suite. And we'll talk a little bit about that coming up. We will have support for the end-to-end lifecycle of data, as I mentioned earlier. So the ability to do ingest analysis, sharing, and publication to not only allow you to go through the workflow, but understand where your different pieces are and what data you have going through your workflow and what's going on with the data stored on the system. And finally, the software stack is really sort of being defined right now. You know, we could try and push out everything that we could think of, but we'd really like to get input from people who are interested in using the system or expecting to use the system to sort of prioritize which software packages are important for people now. So if people have very favorite, you know, things that they would be using from the HPC stacks or from the computational biology stacks that we already support here at TAC, please let us know. Timeline for release, Wrangler will be ready for initial public production use by the end of January of 2015. We will continue to upgrade the system over the coming months after that as the DSSD devices become available for general consumption. These DSSD devices are being released to us about 6 months early, and so the software and systems will be evolving. I wouldn't say rapidly, but I'm expecting some growth in their capabilities in the months following release. We're doing some initial benchmarking, and we expect to have early users on in late 2014. If folks are interested in that, please get in touch with us. And as I mentioned, we are currently working with the 16-node prototype of the DSSD technology to really understand where it is, where it's going, and how we can best use it to improve people's workflows. So with that, I'll turn it over to Christopher Jordan, who's going to talk a little bit about the data management plans that we have for Wrangler.
Okay. So I'm going to talk a little bit about kind of the data management features in general that we'll provide for Wrangler, talk about some of the specific mechanisms that we will provide for moving data in and out of Wrangler, and then talk about some of the IRODS and other data management applications that we'll provide that that are a little bit different on Wrangler versus some of the other systems in Exceed. So there's kind of two primary modes of file management for Wrangler. You've got a basic file system, which is kind of what Niall already described. We've got the Lustre file systems that provide typical Unix kind of mechanisms for interaction. And then we have IRODS, which is a policy-based kind of management system that will provide some more data collections-oriented features and some additional features around ingest and auditing, which I'll describe later. And we'll also provide this data portal that will be a web-based interface that kind of provides a window onto your data stored on Wrangler, so you can monitor in a little bit more detail and control to a certain extent the data that's stored on Wrangler, where it is and what kind of state it's in. So Unix file systems are pretty straightforward. They'll look very familiar to you if you've worked with Stampede or any of the other TAC systems. There'll be the high performance flash that Niall's already described, and the disk system, which won't particularly be slow. It will just look slow in comparison to the flash based system, obviously. And these are provided for support of both analysis functions and data management kind of functionality. So we'll have specialized file systems for various functions. This is again, somewhat similar to what you might see on a system like Stampede or Lone Star, but with a little bit more refinement and with more targeting to the specific characteristics of Wrangler. So we'll have scratch kinds of file systems for analysis applications, places where performance is really important, but it's really a temporary area where data is moving through in that stage of the life cycle. But then we'll also have file systems for specific functions like ingesting data, publishing data, other kinds of functions as we kind of spool out the whole life cycle. And when you put data on these kind of specialized file systems, there'll be particular features that are associated with that, such as the publication file system will be open to the web. So putting data on that file system will be a way of saying, I want to publish this data to the web, and it'll become immediately available. And we can also do certain things with ingest verification. If you upload manifest files, we can verify checksums, ensure that a specific data collection that you're moving into the system actually gets there intact bit for bit. Grid FTP and the Globus Online tools that sit on top of it are kind of the primary method for moving large bulk data into the system. Grid FTP has been around for a long time and is kind of the best high performance general method for moving data between big systems over high performance networks. The servers are all 40 gigabit Ethernet, so that's 4 times faster than kind of the fastest Grid FTP servers we've had typically up until now. And of course, we do have the 100 gigabit network at both sites, so there's a lot of data movement capacity into this system. At least theoretically, you can move 25 gigabytes per second into the system over the 2 networks at TAC and IU. And Grid FTP at least is capable of doing that. So Globus Online, just for those of you that may not be familiar with it, provides this kind of nice web interface for moving data in a graphical form. And this is what it looks like. So you just pick an endpoint. And one thing to note about this, the Globus Connect utility allows you to deploy one of these endpoints on your own system so that you can move data from a local campus system or even your desktop if you wanted to, although it's not necessary. It's a way to get some additional performance if you have systems that are connected with a high-speed network. So IRODS is the system for more kind of intensive data management kinds of functionality. IRODS provides this kind of virtual namespace that sits on top of multiple resources. So in this case, it'll be the disk and the flash and the 2 disk systems, one at Indiana and one at TAC. And you can have more kind of explicit control over replication parameters. You can have additional replicas if you want 2 copies on a particular disk system. Have that that don't necessarily recommend it. And you can also connect it to additional IRODS systems. So we already have an IRODS server on our Corral 5 petabyte disk resource here at TAC, and you can connect it and migrate data in and out of that system pretty transparently with IRODS. And I also talked about the policy-based characteristics. So replication between TAC and Indiana will be automatic. If you store data in IRODS on Wrangler, it'll be replicated to Indiana if you put it on TAC, and to TAC if you put it on Indiana. And it also has metadata capabilities, so you can store more detailed information about all of the files that you store on Wrangler, and Fixity capabilities. So in addition to ingest verification that I already talked about, you can then go back and check at any point and verify that the data is still what it once was. And we have these web-based access mechanisms, some of which are programmable. There's a new REST API. There are also other APIs so that you can programmatically interact with IRODS from within jobs or web services. And this is just a quick view of what the IRODS web interface looks like. And another kind of key feature of IRODS for data management on Wrangler is these data sharing capabilities. So you can do web-based access for intra-group sharing. That's used a lot if you've got kind of distributed groups that all want to be able to collectively curate a collection. And there's also this ticket-based sharing mechanism that allows you to essentially generate a token that's just like a string, or in the case of the web interface, it's a URL, and you just give that to somebody else. And as long as they have that token, they can access that same data. So it's somewhat similar to things you might have seen with Dropbox or Google Drive, where you just have a simple link that you can give to somebody else, and it gives you a sharing mechanism. A key aspect of this, though, is it also gives you upload capability. So you can create an upload folder where you give somebody a URL and they can actually load data into the system without having to have a whole account set up. And these tools are accessible with both the web and the command line. So we have some kind of simple collections management features that'll be available in the data portal that just give you real kind of broad characteristics or features around ingest verification. I already talked about fixity checking, usage reporting. These will all be simple things you can just get to in the data portal and say, show me the kind of average checksum characteristics for my collection, or how many files do I have, and how much data am I using, all those kinds of things. And then with the IRODS collections, you can do some additional rules and reporting with more detail over, for example, different kinds of files. What file types do you have? What are the metadata characteristics? How much of your data has metadata associated with it? Those kinds of things that may be useful for different reporting functions. And of course, IRODS is very customizable. You have microservices that you can write yourself and connect to it, and the rule engine can be highly customized. So you can basically set this up to match any kind of needs that you may have, including automated metadata extraction, those kinds of things. And because Wrangler will support persistent services, something we'll talk about more in a minute, you could theoretically set up your own IROD zone if you wanted to do very detailed customization and plug it into the Wrangler zone, and again, automatically migrate data around, manage data automatically in whatever way was kind of most appropriate. These are things that may require some detailed help, some extensive consultation with the folks here at TAC or Exceed more generally. And Niall will talk a little bit more about this ECSS mechanism you can use to request kind of long-term projects that will support these kinds of customization efforts on Wrangler. So a little bit about custom data services. So there's a lot of newer data management applications that exist as persistent services that kind of utilize different aspects of the Wrangler or other infrastructure. So databases, the file management capabilities I've been talking about, web services, all these kinds of things. And Wrangler will support these. You can run persistent services that are connected to the flash, that are connected to the disk, and you can have all these different components running on Wrangler. Although they don't have to be, you could be running a web server someplace else and connect it to services that are running here on Wrangler. And we kind of have some things that we plan to do already around functional magnetic resonance imaging processing and different kinds of genomics pipelines. A lot of these you can just run on the web and have people upload data and do automatic processing. All of that is entirely possible while still taking advantage of the high performance capabilities of Wrangler. So just a note on confidential data types. Obviously, this is often an issue when you're dealing with data management, as you have whole collections or portions of collections that may have special security requirements associated with them, special privacy requirements. I've talked about we have audit capabilities, we'll have encryption capabilities, and other kind of special monitoring capabilities that will help to support these kinds of collections. But in most cases, the arrangements for these things are not something that we can kind of blanket say, oh yes, we support all private health information or anything like that. So you kind of have to talk to us about it, and we're happy to do so and to work out mechanisms to ensure that data is appropriately protected. And with that, I'll pass it off to Weijia, who will talk about data analysis support.
Yeah, I figured we get questions.
Okay, hello. This is Weijia Xu. I'm going to talk about a little bit how we're going to support the data analysis on the Wrangler. So first of all, I want to reiterate that the Wrangler is a different machine than the typical high-performance computing cluster we have been seeing. So although it's being designed to help people to deal with the big data, to do big data jobs, we set our goals, and we are going to not only support the big data analysis task, but also we want to support all the small data analysis tasks people may need when they're managing their data, when they store their data. So we want to be able to support both small and big data analysis tasks. And also a big difference between data-intensive research or data science versus traditional simulation-based high-performance computing is a lot of research methods require interactivities between users and their analysis and their data. So we take that very seriously. We want to support both batch processing analysis mode, where you can submit in a job for process, as well as a interactive analysis mode, where you can interact with the data analysis. You can go actually see your data, see your result, and interact with the analysis method involved in the whole process. We are going to supporting both very generic data analysis tools, as well as the set of the domain-specific analysis tools, whatever people needed. The lastly but not least is we notice a lot of scientific computing researchers, and they are now using heterogeneous kind of the tools. Those are some of you may using a script to using Python to pre-processing some of your data, and then you call another C program, and then you may use another tools to do the analysis. So we recognize this kind of trend with the heterogeneous program environments. So we do want to providing that, and we do want to give user a more similar integration between multiple tools we are going to support. So with that being said, there are literally like 1,000 of different analysis tools available there. So we cannot install every single of them from the day one. So I'm only going to briefly talk about our plan of the analysis tool support. So I'm breaking this down into, say, we are going to at the day one supporting some of the generic general purpose data analysis software package. Those are including R, VCA, and we do want to provide support for the Python. And also as we move on, as more user come on to use Wranglers, we are going to gradually adding more data analysis support, and we are going to adding more on the project specific or domain specific support on there. Another big component of data analysis support is to support the MapReduce programming model for people to run the big data processings. So let me give you a quick walkthrough on the 3 generic analysis support we're going to give. The first one is the R. R is an open source package. It's freely available. It has been developing in the past 20 years. It's initially developed as a statistical analysis package, but now it's became a very productive analysis tools used in many fields. The core feature of the R, including a very comprehensive set of statistical functions, where you can import your data and run statistical analysis. Then you can run you can do visualization with your analysis, with your data and the analysis results. With more community developed package available, R has begun to have more and more data analysis methods support as well. So it's no longer just a tools for statistical analysis, but they also including a lot of like a data mining method being implemented. The power of the R, one factor is coming from their feature allow community developed packages. So if you go to the R website, there's actually over 6,000 packages now available in our website, and they organizing them into different topics and they call the task views. In the website, they currently have 32 topics. Those topics are very diversified, and they are ranging from the topics on social science to physics to astronomy. So they gave a very good coverage on different type of domain fields. So we are seeing more and more people doing their entire research and doing their research analysis with our package. So for the support on Wrangler is we will make the R core package available for all the users. So we will install them as a module, and then they can a user can just load that module and use it. And we are, along with the core package provided by R, we are also going to install a selected company, mostly company used package. In addition to those, we will setting them up the way so user can easily install the package on their own. So if it's a very specific package there. For the R on the Wranglers, we are also going to providing support for running R in parallel in both multi-core mode and both in multiple and also as well as using the multiple node for the processing. A big usage mode of the R is to use it as an interactive analysis tools. So we will supporting both batch processing usage as well as the interactive analysis usage. So for the interactive analysis usage, we are also going to install another GUI interface of R called R Studio. So the R Studio is a separate it's a separate software. It's developed. It's an integration between the integrated development environments as well as the console environments, where you can developing your code, you can debugging your code, you can profiling your code, as well as running the code interactively. So this slide just show a quick screenshots of the RStudio interface. It breaks up into 4 components. On the top left, where you can see your source code and you can editing them, and you can interactively run any part of the code. On the bottom right is a console of the R, where you can directly type in R command and to run R script or calling AR functions. The top left is a window that shows all kind of like environment variables and all the things, information about the systems. On the bottom right is a view that where you can directly see any graphs you are producing through the R, or you can use it to navigating through the file systems. We are going to supporting running RStudio as well as install the RStudio server, so a user can access can use RStudio remotely through the web interface as well. So for the parallel support of R, since R version 2.14, it's including a parallel package with the core installation. So we will have those available. The parallel package will allow user to developing code that can leveraging the multi-core or multiple nodes. In addition to the parallel libraries, and we are also going to install Intel Math kernel libraries on Wranglers. The Intel Math kernel libraries has a very nice functionality that can directly offload some of the R code using multiple cores available in the system. So the difference between using the Math kernel library versus using the parallel library versus using a parallel package is the user doesn't need to change their current code. They can directly specify the environments and calling the math and utilizing the math kernel MKL dynamically, and then their code can utilizing all the cores available in the system to run that. To help user to run R with the multiple nodes, we are going to supporting the Snow package, which Snow is allow user to constructing a cluster dynamically and used by R. And once the cluster is constructed, you can write in R code similar to the MPI styles R scripts and using multiple nodes. Another parallel package we plan to support is called the PBDR. It's developed by the Oakridge. It's supporting it's also using the MPI library as a interface. It's a low-level interface to do parallelism across multiple nodes. Lastly, is that Wrangler will providing the capability to run Hadoop clusters. So we are also going to providing the support for developing and running our code with Hadoop. There is a R package available called R Hadoop can help user to doing that. The other tools we commonly heard user to use is called Weka. Weka is a software package written in Java. It including a very comprehensive implementation of commonly used machine learning and data mining algorithms. In the recent version of the Weka, it also take a similar approach as R does and allow people it's providing the API and allow community developing the package. So in the past couple of years, there has been like over near like 150 packages that are currently available for people to use. Those packages are on top of the more than 100 data mining methods already implemented with Java in Wekas. In addition to those implementations, the Weka is very user-friendly. It's providing 3 graphical user interface and corresponding to different use case. The first graphical graphic user interface is called Weka Explorer. It's basically an interface that you can open your file, you can do the pre-processing with your data. Once you finish with your pre-processing, you can move on to different type, and each type corresponding one type of the analysis method you could run. So for example, they have a classification type where you can run classification analysis, and then they have cluster association and the feature selection types, and for you to, so depend on the user needs, they can select in different methods that already being implemented and do a quick run to see what the result looks like. The last type on the Weka Explorer is to visualizing the results. So if you're doing a classification or doing clustering, the result can be directly visualized as a tree structure or as a graph. The second Weka GUI user interface is to supporting the workflow. It's called the knowledge flow. Basically, you can specify a modules that conducting a certain analysis task and this form a pipelines. Then if you have a fixed usage scenarios, you have different you have a lot of data, or you have data coming periodically, you can define a workflow. If you can define a process pipelines with Wekas, and then whenever you have a new data, you can run them again with the same pipelines. The last GUI interface the Weka provide is called experimenter. So the experimenter is a similar way how helps user to run jobs in batch. In this case, is if you have one data set, but you are not sure what type of methodology is best or what kind of parameter is best for that data to conducting data analysis, you can use experimental views where you can specify multiple data analysis methods being applied to the same data set, or different parameters being applied to the same parameter to the same data set, and run them in a batch mode. Then later you can comparing the result and selecting which method might be better for use. So we see the Weka is a typical example where the user may want to just do a small data analysis task, or they have a large data set but want to have a quick sample to help them to know their data better, or to selecting which method are better for this particular data set, or meets their analysis needs. Weka is written in Java, so it's also available as a Java library. You can use them with your own customized analysis code. To support Weka on Wranglers, we will providing a module for Wekas. Then user can run the Weka remotely. It can either through the VNC or through the web portals. You can interact with the GUI interface directly, or you can write in your own Java code and directly using the Java API to using the Weka as a libraries. We are also a nice feature about Weka is that it has an interface to other programming language and other analysis tools. So there's a Weka to R interface, and also there are Weka to Python, Weka to C, and Weka to other programming language APIs available there. Starting with the Weka 3.6, there's a distributed implementation available for some of methods that can leverage in the parallel processing capability available on Wrangler as well. There are also a MapReduce interface called distributed Weka Hadoop package available now, allow people to write in a Hadoop jobs using the Weka package. We have been supporting the Python in many other HPC systems. So there's typically we have like around 180 Python packages that are installed with the core Python module we are going to providing. Those some of company use package we included in the Python installation, will including the SciPy, NumPy, and scikit-learn for data minings, and NLTK for natural language processing. MLPY is a Python library for machine learning. The Network X is a Python library specialized to do graphic analysis and network analysis. For the usage mode, a user can submitting a batch processing job with Pythons and to run them in through the command line interface. Or we are also going to providing the IPython notebook as to help people to run them interactively. The IPython notebook can also going to be available through the web portals, so the user can initiate IPython notebook sessions through the web. Similarly, the Python also providing interface to other tools we are going to providing like R, Weka, and Hadoop as well. So that's about the general purpose of data analysis support we are going to providing from the day one. We are going to adding more as people need it, especially for the project or domain specific needs. So we recognize some of common usage, say the workflow tools might be used by a lot of research projects, but a lot of those workflow tools is highly customized. So we may not be able to providing a general installation at the day one, but we will providing those support whenever a project is required and needed. So we're planning to provide support such as using Kepler or using Swift to organizing the workflows. We are also going to providing the domain-specific analysis tools required by the user project. Tech is already involved with the Galaxy support, so in a lot of like bioinformatics or SQL analysis, using the Galaxy to organizing and do their analysis works. The Wrangler will have the support for the Galaxy as well. The bioconductor is another very commonly used bioinformatics toolkits that leveraging the R. So we we will have those support ready from the day ones, but we can have more of those supports if there's an actual project and actual users that really want to take advantage of them. So lastly, it's not just the software support we're going to providing, and we are also having a staff that are knowledgeable with those software, with those technologies that can help the user to selecting which methodology or which tools that are best suited for their analysis needs, and can help them to do performance tuning and find out where their bottleneck, and therefore developing a new scalable implementations. The extended collaborative support will be available through the ECSS as well, especially for the software part. And if you are interested in using Wranglers and you do not see the package your company use being covered by us, feel free to contact us so we can install them in the futures. Next, I'm going to quickly cover about like what's the MapReduce support on the Wrangler looks like. So the MapReduce is now became a kind of a buzzword and for the big data processing. So basically, all the big data processing core is leveraging this MapReduce programming models. The MapReduce programming model is actually very simple. It's just a define a platform or define the model has a two core function. One is called map. Essentially, is to distributing your workload into smaller pieces, and it's mapped to each workers. Then it has a reduce, which essentially is similar to the collect function you may be familiar with. Is getting the result from all the mappers and then putting each individual result together and form a larger results. So the MapReduce programming model is used extensively for the big data. Is because it's different than the current HPC programming models. Biggest difference is the map programming model is trying to move the computation to the data instead of fetching your data to the compute node. We will have the computation and the data has co-located in the same node. So that will match well with the Wrangler infrastructures. And also the MapReduce programming models is trying to avoid random access. It's more taking more advantage about the data localities to speed up the processing at a large scale. So this figure is just shows sort of a generic model of what the MapReduce looks like. They leveraging a data structure called key-value pairs. Then the implementation can map in the key-value pairs to be processed into different worker and processed into different threads. And then the reduce phase will be responsible to merging those results back to form the final results. One of the most commonly implemented MapReduce programming model tools is a Hadoop. It's everybody familiar with that. It's a library to enable efficient distributed data processing. Hadoop is an open source project, but now it's no longer just the Hadoop one particular libraries. It's actually a Hadoop ecosystem, help people to do the big data processing. So it typically forms with including things like the low-level Hadoop distributed file systems, and Yarn is a MapReduce distributed processing framework, is taking care of the resource management. On top of that, there's several high-level applications available, like pig scripting, allow people to easily writing scripts. It's a scripts language for people to developing MapReduce job, and Mahawk is a machine learning library that works with Hadoop libraries. It has a connectors to other analysis like R or to the database. We want to supporting as many as product from Hadoop ecosystem, but at the day one we are not going to expect to have a full support. You see here, full like every single of the software package available on Wranglers. We are going to start with the support on things like the big license, which helps people to quickly writing and MapReduce jobs using script type of language. We are going to providing support on the Mahawk, which including over like 50 different algorithms for the machine learnings. You can use it as a library to develop your own Hadoop code. It also has a command line interface where you can directly call the existing functions through command lines and doing your analysis. We're also going to providing the Hadoop streaming support, where we can using that interface to utilizing an existing Python code and to do the analysis using Hadoop clusters that can essentially automate the distributed process, analytic process. The Hadoop is just one model, one implementation for the MapReduce programming model. And as time goes on, there's more technology coming up. So a lot of like new buzzwords like the Spark and GraphLive, which is more, GraphLive is a library that more suitable, is specialized for graph process and graph analysis. We have planned to have them have those software available on the Wranglers as well. So especially if you have a particular needs or you're interested in using Spark or GraphLive, be sure to let us know so we can get those ready. We can deal with the user needs and we can get them ready for user to use. Similarly, if you need any other big data processing tools that are available, you simply should install, and feel free to let us know. We'll be happy to investigate and evaluate the possibility to support them in the futures. So with that, I will turn back to Chris Jordan for the database support.
Okay, so another kind of novel feature of Wrangler will be the introduction of database support, both in a kind of persistent service mode and as temporary databases as part of jobs. And so I'll talk a little bit about that and just introduce kind of some of the basic concepts. So you may have heard the acronym SQL. It stands for the Structured Query Language. It's a standard that's been around for a very long time. It's been around for a very long time because it's very powerful and it works very well for highly structured data. And it allows you both to interact, to define and create highly structured data, to define schemas for data structure, and to interrogate data structure and to interrogate data. And there's a lot of kind of data mining and data comparison operations that you can do really entirely just with the SQL language. So one way to look at a SQL engine, which typically are known by this acronym RDBMS, Relational Database Management Systems, is as a kind of very powerful application in itself for storing and interrogating data. You may not need any additional data analysis applications. So as I mentioned, typically RDBMSs are kind of basically engines for operating with SQL. Postgres and MySQL are the ones that we know will support from day one. There are many others. MonadDB is one kind of particularly popular in research fields that we will support as they're needed and as requested. You may also have heard NoSQL, especially in association with the big data buzzwords. Basically, the point of NoSQL here is that the SQL and RDBMS engines have a number of characteristics around data consistency, enforcing particular kinds of structure. And what NoSQL engines do as a very broad generalization is that they allow you to trade off kind of one or more of these characteristics in return for a certain amount of scalability, a certain amount of performance, in some cases reliability. And basically, because there are so many of these, typically what you need to do when looking at NoSQL options is pick something that kind of matches the structure of your data particularly well. So I've listed a few kind of common examples here. So columnar data, basically a SQL or RDBMS engine will tend to look at your data as rows. So the kind of common example is an address book where you have a bunch of addresses with names, first name, last name, address, city, zip code. If you take all of those things together, that's a row. But if you want to look at primarily just the zip codes, then you might choose to encode your data in a more columnar format because that allows you to operate on it in the way that's most natural to you. Key value pairs is another very common one. Hash tables are an example of this kind of thing, but there are very, very big distributed versions of these. Sometimes you've got large amounts of XML encoded or JSON encoded data, and there are tools like MongoDB that operate natively on these data structures. And basically, the idea there is that you're kind of dealing with semi-structured data. There is a structure to the data, but it's not always consistent from record to record. So there are different kinds of modes that you might want to use a database for. I mentioned, in many cases, you may be able to do your data analysis tasks entirely within a database. And so in some cases, we've seen applications that basically just consist of sequences of database queries. And it may look like an application outside of the database, but really all of the work is being done inside the database. You also have kind of persistent databases that basically support data collections or data collections as resources in their own right, where you want to query the data in a persistent way. It's always available to you. And those may be public databases that anyone can access. You may also want to do different kinds of stream processing. You may have sensors that are constantly generating data or data that's being generated on a nightly basis, and you may want to ingest that and have a kind of constantly growing body of data that you're going to work on. So those are some examples of where you might want a persistent database. You may just need a transient database that's kind of part of a job. You may just start up a job, create a database, put some data in it, do some processing on it, and then kind of tear it down. SQLite is a library that's often used to do this. If you're working with a reasonably sized amount of data and with the high performance Flash engine that we have on Wrangler, that may actually be a pretty reasonable option. But you could also stand up and tear down things like MySQL and Postgres as well. So both of these modes will be supported on Wrangler. Just briefly, one of the kind of nice characteristics of databases is that they often give you a very granular view of security within the database. So rather than a typical file kind of database security mode where there's the same permissions applied to all of the elements within the file, databases will allow you to provide more detailed control on a kind of per table basis, in some cases even on a per row basis, on a per host basis based on where a query is coming in from, all those kinds of things. And oftentimes we use the term roles to group sets of those permissions together. And the DB administrator is kind of the common role for the super user within the database. And that role has kind of global control over the schemas and the data within the schemas as well. And in some cases can also set access controls. GIS, geographical data, is a common application for databases. It's kind of important to note that this kind of data can now be useful in a very wide variety of fields. Not just geographers are interested in this data anymore. So biology, ecology is kind of a good example. Sociology, we have interesting projects that are looking at the interaction of climate change and social disturbances in various parts of the world, and that relies on having detailed geographical mapping of both weather patterns and events and being able to correlate those kinds of things. And then, of course, urban planning is an area where GIS data PostGIS, which is a set of extensions to Postgres, but you don't necessarily have to have or use something like PostGIS. GIS data is another example of a type of data that might actually work very well in a columnar kind of database. There are lots of different systems that may work well with GIS processing and lots of different options here. So a couple notes about bringing a database application to Wrangler. there's a lot of different aspects of I/O performance, and databases tend to touch lots of different aspects of I/O performance. They tend to have lots of different options in terms of how you make use of memory, underlying storage, all those things. And you can put different pieces of the database and different parts of the data collection on different hardware to kind of match that I/O needs. And one of those hardware components could be memory as well as flash, depending on what the need is. And so it's kind of important, both in terms of writing a good allocation request and in terms of getting the best performance out of Wrangler, to kind of understand what the mix of different performance factors is and the performance of your application that uses a database. Just another note here, databases are often parts of larger systems of network data services. So GIS layers, again, are an example where you have a database storing GIS data, and then you have a service that sits on top of it that actually serves kind of processed versions of those. In some cases, just serves images, so maps is a common example there. And Wrangler will support persistent services and the databases that sit underneath them. I talked a little bit about this before, but kind of the key thing is here, if you want to use Wrangler for this kind of function, then the database piece really needs to be kind of a significant part of the application. So it's really common in almost any kind of web application to have a database that's used to store user accounts and passwords. If that's all you're doing with the database, then it's probably not a good candidate for sitting on the high performance flash tier on Wrangler. About Wrangler and supporting the NoSQL databases, there are a lot of these out there in a lot of different kinds of formats. There are quite a few that I haven't even mentioned, and if I mentioned them all, I would run out of time long before I got through them all. So one of the things that we're going to do here is really support the technologies based on the user demand and user need. So we're really encouraging you, if you have a specific technology that you want us to support, or you have a specific need and you don't know what the technology is that would best support it, that you kind of express interest, you get in touch with us, talk with us and with Fixity representatives, and make sure that we know that you have these kinds of needs. And we're always happy to kind of walk through scenarios with you and try and help you understand how to make the best use of Wrangler to accelerate your application. So I mentioned before, we have this data portal. The data portal will allow you to do some kind of minimal provisioning and configuration of databases. This will get more complex over time, but initially you'll be able to kind of say, I want a Postgres database, give it a name, tell us if you want it to be a public database. So if you want to create this as a public kind of data collection resource that anyone can access, you can designate it here. And you can do some simple role management. So I talked about having that database administrator role. So you can, if you have somebody that's kind of designated in that role, then you can select that in the portal and have all of that setup be done for you automatically. Just another kind of note here, a lot of times people come to us and they know that they are going to need a database. They have kind of semi-structured or highly structured data. They may have, just tons and tons of Excel files or comma-separated value files, text data, and they need to do more kind of detailed development, understand the schemas, put together the database and application that's going to operate it. We are kind of happy to work with you on those things, particularly if the goal is to build a collection that will then be used by others as a data resource. So you can build up these databases that then become resources for other researchers. And then you can build services that operate on those and provide more detailed information to people. And the Exceed ECSS program, which Niall will talk about some more in a minute here, will provide some support for these kinds of collaborations. And so we want to encourage people who have these kinds of problems to go through the Exceed process and to request ECS along with Wrangler, so that we can work with you to kind of build these more complex applications. And with that, I'll pass it back to Niall, and he'll tell you about how to get an allocation on this fantastic resource.
All right. Well, we're doing well on time, so I'm glad to see that. Talk a little bit about how we're allocating Wrangler. Wrangler is, as I mentioned earlier, part of the ACI program from the NSF, and so it's allocated within the Exceed ecosystem. So 90% of the cycles and storage on Wrangler will be controlled by the Exceed project and the XRAC allocation process. There will be two different allocation paths for getting going on Wrangler. The first is a startup allocation. Startup allocations are small allocations that are available to sort of new PIs to explore the capabilities of a new system to them and demonstrate that this fits well within what their needs for doing their research. These proposals are accepted anytime once the resource is available. And as I mentioned earlier, we expect Wrangler to be available in January, so startup allocations would begin to be accepted come January 2015. There's also the normal allocation process, which are for larger allocations. And these are really the allocations that we wish to have for people to support the computational needs for their research projects once they've demonstrated that they've been able to do things. These would allow people to have more of a larger allocation and a longer term, possibility of longer term storage and preservation of the information. These proposals are accepted 4 times a year and are reviewed by a review panel called the XRAC. I may drop into jargon at different times, so I'll try and define them up front, and are granted 4 times a year. So we have an upcoming cycle, I believe, starting in January 15, somewhere around there, which will be the next period in which long-term Wrangler allocations will be accepted. Which is what I said on the next slide. In addition to the just asking for time, though, Exceed has the extended. Is there a question coming in?
Yeah, are you going to talk about allocations for star partners?
Yeah, we can. So I think might be a little input from you on that.
They can just go to the DAC portal.
Okay. Okay. So
Yes,
it's,
finish your spiel. And I'll
let me finish my spiel, and then Dan can cover that. But the extended collaborative support system through Exceed will allow folks, while they're requesting time and storage on Wrangler, to then also justify the need for collaborative support with the support staff in the Exceed system, and many of those folks are here at TAC, to get their projects going at a scale that they may not be able to individually. And so that process involves you ask for the extended support, but then once that's granted, a formal plan is sort of worked out through with PI and the collaborative folks here at TAC or in the rest of Exceed to come up with a plan to move forward that is well enough defined to pretty much help us have a successful conclusion to whatever the collaboration is. It's not really a project where you would hand us what you need to do and it would get done. It is not collaboration as a service. I think you might put that in modern terminology, but it really is to form collaborations between projects and people with the technical expertise to help get these things going. So when you're proposing for these longer period proposals, that's the time when you would ask for ECSS support. Nothing better than pictures of web pages that you can't really do anything on here, but this is just to sort of show you that the Exceed website is available, and then under the User Services tab, you can get to the allocations overview. And this is where you would go in to get started to understand, how to request some of the information I'll go over here, what the policies are, but then the step-by-step guide to actually get the allocation pushed forward. And then the TAC user portal, which is for the University of Texas as well as UT system. And I take it from what Dan said, this is where star partners would come as well. Be able to come in and ask for allocations on Wrangler from here. And underneath the allocations tab, this is where the project and allocations is. You can come in here and actually ask for time on Wrangler, and you'll see, indeed, the Wrangler team has an allocation currently going right now on our VM farm. But These are sort of the mechanisms that you go through to do this. The way that time and storage are allocated on Wrangler are a little different from how we have things on most of our HPC systems. There are actually two distinct allocations that are requested. The first is a compute allocation, and the compute allocation is a little bit of an overloaded term here, but it's requesting nodes to run analytics or other applications on in the analytics cluster. And because the flash memory that I was talking about earlier is connected into those resources, part of the compute allocation also is requesting the amount of storage that you need on the flash storage system. These are basically allocated in units of node hours. So each for your processing, if you need up to 4 terabytes of flash storage or up to 24 processors or up to 128 gigabytes of memory, you would ask for 1 hour of time. Now, I mean, we don't expect people to be asking for individual hours. Multiple hours is where it starts to get interesting. And I'll go into some examples to show how you might calculate this based on what your anticipated workflow is in a minute. If you are indeed using sort of flash storage with some of the dedicated servers that we have, you would still request things as part of the compute allocation here to get the flash storage. In addition to that, in order to use the back-end Lustre longer-term file system, there's a storage allocation that's independent of the compute allocation, where users would request the amount of storage they need to both ingest, work in sort of the scratch fashion that Chris talked about, and then eventually move into sharing and preserving their information. This is also where some of the dedicated database servers would be running to use the spinning disk storage in their back end. And so in cases where all you need is spinning disk and dedicated services, a storage allocation is what you would ask for alone. That said, for most projects, we anticipate people needing both, because they will need to be able to have their data be brought in, hosted, and then migrated onto the systems as they're doing their compute, and then pulled off of the flash storage systems once they're finished. So we really do anticipate everyone asking for quantities of both allocation. As far as Hadoop is concerned, we will be rolling essentially Hadoop clusters to people on the fly. If you need to have a Hadoop cluster with a particular capacity for computations, a certain number of data nodes, as they're referred to, you would ask for a compute allocation that covers the amount of compute that you need, or again, the amount of DSSD storage you need on the back end in order to fulfill your compute. And I'll have a brief example of that coming up. In fact, right here. So the first example is, say a user needs to run basically 300 map jobs on about 80 terabytes of data, and estimates the job will run in about 2 hours with 240 mappers. You can go through and calculate those 240 mappers would map out across the 24 cores of each system, running for 2 hours, and with those threads in parallel would require about 6,000 hours of compute time. The flash storage parallel on that, though, is that you need 80 terabytes. So 80 terabytes divided by 4 per node times 2 times the 300 different jobs gives you need 12,000 compute hours to request that much flash storage. So in the end, you would go through in this one and request your 12K of node hours to cover the flash storage need that you have. If, say, for example, though, you needed a third of that in storage, of course, that would flip over and you would request based on your CPU limitation. Won't go through all these in as much detail, but here's an example where you need to have 50 nodes due to the memory constraint to mine through 120 terabytes of text data for a month interactively. And it's not surprisingly, it's a small amount of data, but a lot of CPU over a month. And so you would go through the calculation and find how many node hours you need based on that. Last one is sort of, again, doing math for folks here, but would you have sort of a project that is perhaps producing data periodically, every day over the course of a year. And so you might need to have a terabyte per day of space of flash memory accessed over a 12-hour period each day, with 48 threads to process that data. So say maybe this is processing, urban, collected traffic flow data or astronomical observations. Go through, once again, sort of running the same sort of numbers, and you find that you were limited in this particular case by how many CPU node hours you need, and so that would be how many node hours you would request. Once allocated, Chris mentioned the data portal, which will allow people to be able to, get their own databases allocated within the server and designate, who the database administrators and control those sort of things. And for the analytics systems, we sort of anticipate a need for more of a reservation system than a job-by-job system for handling people's analytics jobs. Doesn't make sense to stand up a Hadoop cluster for 15 minutes. It's much better to stand it up for a few weeks so that you don't have to transport your data in and out of the flash storage, essentially defeating the purpose of the flash storage system. So we'll allocate nodes for these, what we're thinking of as campaigns, where people might have many nodes for many days. This minimizes the transfer and allows both for interactive and for these sort of campaign-based processing needs, such as, as I was saying, if you're running an astronomical project that has measured data coming in every day, a reservation would be very handy to make sure that you have the processing there that you need. I just note you can reserve for the duration of your entire allocation. So if you need to have 5 nodes for a year, if you can justify that need, then that is something that we will support to allow people to do the compute that they need to. We are currently working with a group of folks on some early user work as we roll out the system. We expect that to begin sort of in mid to late December as the hardware starts to arrive and is integrated here at TAC. There are various other folks here listed, but we sort of are thrown out just in case there are people out there who would like to have early access to Wrangler to explore what the system can do for them and how help us as we're moving forward. Please keep get in touch with us, and we can work things out. How to get in touch with us? There are several websites. So you have the Exceed website and the TAC website listed there. In addition, the data at TAC email address goes to all of us within the data group. And if you really want to get a hold of me for some reason, there's my email address. And in addition, we will be at Supercomputing 14 next week. And we will be in the TAC booth and able to talk to people about where things are going, how things are going, and how we can fit Wrangler into your research needs. And Dan's creeping up here.
Star before we go out. So yes, we'll be taking star allocations on the system. As per normal, we'll take about 10% of the allocation on the system and set it aside for industry partners and industry use, as we normally do. There is one difference from our other systems for industry folks, because Wrangler is physically a distributed system with part of it run here at TAC and part of it run in Indiana, and we want there to be people to have accounts on Wrangler, not a Wrangler TAC account, a Wrangler Indiana account, and other confusion. We're going to use the Exceed account mechanism exclusively. At least that's the current plan for all users. So if you're a current TAC Star partner, that means industry affiliate for those of you who aren't Star partners on the phone, and you would like to use Wrangler, you can come through the TAC portal and request an allocation in the usual way through your Star account, but we will ask you to go to the Exceed portal and create accounts there, just so we can synchronize the user ID space and ownership and permissions and everything between Indiana and TAC and your Wrangler account. The files that you own at TAC, when they get mirrored to Indiana, will be the files you own at Indiana and things like that. So, so if you're a normal TAC user and you have a TAC account, we'll just ask you to go to the Exceed portal, set up an account. It's a 2-minute process, but all accounts will be Exceed accounts. So that's the only real wrinkle in that. So does that answer the question for the person who was asking on chat? Or, yeah.
Yeah.
Yep. So
there's a 30 or 40-second delay. So
that's awesome. So at some point,
so we can
I'll find out if the question was answered. So feel free to send us a follow-up note on it. But yes, you can get on with just one extra step. So.
And so answering that one, if there are any more questions, sort of open it up to the floor. And as we have this lag, I don't know.
I will tap dance.
I will tap dance without video, so everybody at home will enjoy my dancing skills. So we'll sort of hang out here for another 3 or 4 minutes to see if there are questions, and then wrap up.
You guys are ready? There were 10 people on the legal session. Unbelievable.
All right, so well, as there are no more questions here directly, I think rather than stretch this out, I will just go back to this slide here and say, if anybody has any questions that they want answered asynchronously, please feel free to get in touch with us at any of these paths, filing tickets or sending us email, or stopping by at SC and talking to us in person. So look forward to hearing from everybody, and look forward to a lot of the great research that's going to come from Wrangler.